Okay, so I'm going to continue now with the second bit of this lesson. I stopped because you probably saw somebody appeared and was looking over my shoulder, and she thought she wasn't in the video because she didn't see herself on the screen, but I'm looking at the presentation on the screen. So I stopped just so I could say hello to my wife. Some of you will probably know her. Going to continue now. Right, now this next little bit gets a little interesting because it's all about angles in triangles. What I'm aiming for is I'm aiming to work out this angle here, which is going to be theta 2, for me to use Snell's law with n is sine theta 1 over sine theta 2. Now, I already know n, the refractive index, from the last bit, 1.47. There it is, 1.47 on there. I know that n is 1.47. If I can work out this angle here, which is theta 2 for this beam of light going out, then I can work out angle C. Now, angle C is theta 1. This is theta 2. I haven't got enough space to write it in, but it's repeated. It's theta 2 is always inside the material. Theta 1's on the outside. If I can work out that angle, I can use Snell's law to work out that. And then if I know, that, the next question says, work out this angle D. Now to do that, I've got to somehow work around this triangle here. Okay. Now I know theta 2. I know theta 2. Because I'm told it's 26. So this theta 2 is 26. So if I'm clever, I can work out this angle. Because if theta 2 here, we'll call this triangle X, Y, Z. I've got a little triangle here, X, Y, Z. If theta 2 is 26, okay, then I can work out this other angle at Y. And how do I do that? Well, I know that the angle between the side of the material and the normal is 90. So this angle here, opposite Y, is 90, take away theta 2. I think I've got my letters wrong because I should have had D, C, B, A, I'll call that angle Z. I've got my letters wrong. I didn't allow for enough letters. I'm going to call, no, that can't, that's Z. I'll call it alpha. Call it alpha. Angle alpha is 90, take away 26, because I know that those two, alpha and theta 2, add up to 90. So 90 take away 26 is 64 degrees. Right, if I know that alpha is 64, then I can work out the size of this angle here, angle B. Now, how do I do that? Because you're already told that this is an equilateral triangle, that angle is 60, that angle is 64, this angle, remember all angles inside any triangle add up to 180, so B, add alpha, add 60, that's in this triangle, XYZ, B plus alpha plus 60 is also equal to 180. Now, I know that alpha is 64. So I've got B added to angle alpha 64 plus 60 is equal to 180. So I now know how to find B. So I take 60 and 64, that's 124. I take that away from 180. So B is, you can do the maths, 180 take away 124 is 56. Right, so if I know B, which is 56, I can now work out this new theta 2 for the ray of light leaving. So the new theta 2 is 90 take away 56. This is really involved, but it's not difficult. It's really involved. Okay, so I'll then move on to this and say that this little dot here, this is theta 2 for leaving. This was theta 2 here for coming in. This is theta 2 for leaving. It's this little angle here. So theta 2 going out is simply, because again, the angle between the side and the normal is 90, is 90 take away 56, which is 34 degrees. So I've just transferred angles around from here, starting here, finding that one, adding these three together, finding that one, now finding that one finally. Theta 2 is 34. Theta 2 for leaving is 34. I can now calculate angle C, which is theta 1 on its way out. And I do that once again. So I'm going to find angle D. That's what the question says. Find D. But first get angle C. Okay, and I can use N equals sine theta 1 divided by sine theta 2. You can see that this whole refraction unit is just about this really big formula that's on the data sheet. I know that N is 1.47 because I've already done that. So I can do 1.47 equals sine theta 1 over, now sine theta 2, that's the angle that I worked out last there. It's 34 sine of 34 degrees. I could say that that is angle C if I wanted, because I've already said C and theta 1 are the same. All right, so I'm going to swap over the whole formula. I'm going to get sine theta 1 is 1.47 multiplied by sine 34. And you put that in your calculator, and that is equal to 0.822. And then theta 1 is the inverse sine of 0.822, which is 55.3 degrees. Okay, so C is 55.3. I'm just going to put that on there, 55.3, because I've just calculated it. So how do I get D? Once again, C add D, 90 degrees. I'll go up here. C plus D is equal to 90 degrees. So that is 55.3 plus D equals 90. So D must be equal to 90. Take away 55.3, which is 34.7 degrees. There you go. So not only are we using the formula, we're using a whole load of basic trigonometry or geometry. I suppose that's the trigonometry. It's basic geometry, and remembering that angles in triangles add up to 180 degrees. What else could we do with that? Well, once again, we could look at the variation of what sort of things could they ask you to explain. Well, what happens if I change the refractive index? I change the refractive index. What's the effect on anything else? And you could work through that and say, well, okay, if this becomes bigger, for instance, say 1.55 is a little bit bigger than 1.5. It's supposed to be glass, but you can have different refractive indices round about 1.5. Say that went up to 1.55, that would make that 1.55. That would change the whole thing about the angle that you worked out when it went in, and you'd have to go back and start all over again and work out what's happening, and then you could work through, and that would give you a different answer at the end. So I'm not going to do that because I've had enough of sine theta 1 and sine theta 2 and everything else, and I think we're going to move on to something else now. And something else is, I've touched on this before, is everyday applications of refraction, things like rainbows and water. I did some little sketches about diamonds before. We could have a quick look about applications. How do rainbows work? So I'm just going to finish off on that. I was going to do this as a separate video, but I'm just going to carry on and stick it all in this one. So applications of refraction. And there's a poster on the back of my wall in room 32, and it's got this picture of a raindrop. So here's a big raindrop. We'll make it circular. It's possibly some sort of like tear shape, and we get some sunlight coming in. And what's going to happen to the sunlight? Well, you draw a normal line there, and this is white light coming in here, and you're going to get, first of all, some sort of refraction, and you're going to get some red here, and remember that we're going to get some violet down here. What tends to happen here is that you get total internal reflection occurs here, and this red beam reflects down here, this violet beam reflects down here, and then so that makes this red and this violet, and then it refracts back out, and violet would come out here and red will come out here, and you'll get Roigabiv upside down, Roigabiv, and you'll see a rainbow. And if you look at a rainbow and you're over here and you're looking at it, you'll see that red is at the bottom of the rainbow, and the rainbow is caused by millions and millions of rain droplets, and all those rain droplets all in different places, up and down and left to right and forwards and backwards, will actually give you this whole rainbow effect. Red at the bottom, violet at the top. Occasionally you get a second rainbow, which is upside down from that one. That's a little bit more complicated. And the light, I think, gets totally internally reflected twice somehow, and goes up here and then down here and then comes back out. I'm not quite sure how that works, but it doesn't matter. This is your primary rainbow, and you're far more likely to see this big bright rainbow, and then you might see the second one, which is different, upside down. Violet on top and red at the bottom of the rainbow. Interestingly, every person sees their own rainbow, and the rainbow that you see, somebody else standing slightly to the side of you will see a rainbow in a slightly different position, because of the way that the light comes back to you as an individual and enters your eye as an individual is different from the light that comes back to somebody standing next to you. So that's just one idea there. That's one sort of application. These are sort of weather things that people have been looking at over probably tens of thousands of years, but didn't really know anything about refraction and total internal reflection. And starting off with Willebrord, Snell back in the late 1500s. So you've got that's one application. And what you should do is just make a few notes about that, possibly with the diagrams. What you what else we could look at, also to do with weather phenomena, it's not so much weather, but it's a natural phenomenon, is if you see the sun coming up in the morning and setting at night, the same with the moon. Just as the sun and the moon rise, or the sun and the moon sets, the sun and the moon don't look round. Up in the sky above you, the sun would look round up in the sky, but at sunrise and sunset, that's really exaggerated there. You tend to get the sun and the moon look more oval, and that's to do with how you see the light entering the Earth. Now, the Earth's got an atmosphere around it, and the atmosphere is thickest, it's heaviest, it's most dense near the surface of the Earth. And as you move further and further away, the atmosphere gets thinner and thinner. It gets less and less dense as you move away. So that means that the light traveling through these different layers of the atmosphere, remember, less dense doesn't bend the light so much, more dense bends the light more. So you're going to get, actually, we know the sun is round, but the light coming more directly through all the atmosphere gets bent differently from the light from below the sun, which enters the atmosphere at a different angle. So the refraction is different because of the varying densities of the atmospheric layers. So that's another phenomenon. So basically, most of what you see going on around you is physics, weather patterns. I won't go into all this really, but the best weather observers and predictors are physicists, because they need to have an idea of pressure systems in the atmosphere, heating effects of the sun on the land, heating effects of the sun on the sea. Which way is the wind blowing? Is the wind coming across the land, which it makes the air drier? If it's coming across the Atlantic from the southwest, the air is wetter. How does the geography of the land affect the weather? So most of this sort of stuff is physics. None of that really about weather patterns and clouds and which way the wind's blowing. It fits in with this applications of refraction, but you could do a little bit of research if you wanted to look at why and get a few more notes. It's all to do with the densities of different layers and how the light is refracted when it comes into the atmosphere. Right, I think that is going to be just about it. What you could do now is, if you haven't already been doing this, is you could have ignored all these videos. You could have looked at the notes. You could have looked at the summary notes, Campbell Robertson summary notes, the scholar notes, Mr. Garrett's course notes. I've not looked at the course notes at all. I've not done problems from the course notes, but they're bound to coincide with the stuff we've been doing. You will be looking at some exam questions in due course, and there are naturally loads of exam questions in the block test. The block tests are made up entirely of exam questions. So it's really, I've not structured this particularly well for this refraction topic, mainly because I would normally have all these lessons prepared in advance, because I wouldn't have been in school with pupils, which has made being in school and doing these lessons at the same time almost impossible. And I think that's the same for most teachers. So I thought I'd better start with posting up the refraction work without the videos, and then follow up with the videos. It's now 3 o'clock. I've been producing these videos non-stop virtually since about 8:30 this morning. And I'm going to, it's a nice day, I'm actually going to go and sit in the sun. I'll leave you to it. It's obviously going to take you much longer than me to do all of this. I have extended the due date for the refraction assignment, and I've now put that back to Friday afternoon at 4 o'clock. So you should really be wrapping up your photoelectric effect stuff by now. and you should be progressing on to refraction, working through the whole refraction unit, subtopic I should say, and getting everything done. There's a huge number of Campbell-Robertson problems. You do not have to do the whole lot if you cannot manage in the time. I know it's physically difficult for you as well, that you are required to be in school on various days, and then you get to go home on various days. You've got to, if you're in school, what we've tried to do is let you get on with the online stuff, but inevitably people have been asking me questions, and every day people come in and you're asking the right questions, but it's the same questions. What's going to happen with our exam? What's going to be in our exam? How long is it going to be? How many papers are there? When's it going to take place? Are we going to finish the course? And these are all questions which quite rightly you should be asking. I don't have the answers for everything, but if you have not been in school yet, then well, by the time you get to the end of this, you probably will have done, and you'll get some of the answers, and you know some of the answers. You're getting a full 3-hour exam in 2 papers. Paper 1 multiple choice 45 minutes, paper 2 written questions 2 hours 15. That will probably be in the middle to the end of May. And we're now firmly in the middle of March. So we've got 2 months to finish our last 2 subtopics. And it looks like it's about a week per topic. Photoelectric effect was last week and part of this week. Refraction is this week and next week. I'm then going to go on to a topic called spectra in week 3, otherwise known as purple week number 2. So you're doing photoelectric effect now. In purple week 1 stroke 2, you're doing in orange, you're doing this radiation, and that's like week 2 into 3 is radiation. I will be posting up, I won't be posting up any more videos until the middle of next week, but then you'll be back in purple weeks. That'll be 3 and 4. It depends how much photoelectric effect you've got on. I had originally hoped you'd do photoelectric effect in this first purple week, radiation in the orange week, and spectra in the last purple week of the 3. It looks like it's probably going to overrun because this is running into week 3 there. If you can't get this finished by the end of next week, orange week, then it's no big deal. You can move it into the 3rd week, and you may not start spectra until part of the way through week 4. Now, I know you've got 2 weeks Easter holidays, but you know that the big exam is coming in the middle of May. So we're the middle of March now. This is going to take us to the end of March, beginning of April. You're going to return halfway through April, and then basically it's a month after Easter when we will be doing the last little bit of the course, which is called interference. Hopefully that will be out the way by the end of the 1st week back after Easter. And then we've got 3 weeks of revise, consolidate, revise, get tested, little tests of 40 minutes, but exam question tests covering bits that you haven't been tested on for a while, like our dynamic universe, electricity possibly, and then some final tests on the whole of particles and waves. And that will take you nicely right up to the middle of May when your big exams will be. Okay, I can't give you any more accurate dates than that because I don't have any just yet. Nobody does, but you will be getting information later on. It's giving you a rough outline of what's going on. So finish photoelectric effect this week, please. Start radiation this week, going into the orange week next week. run that as long as you can bear, and then Spectra for the last week. You might have to do some stuff at Easter. Every Easter people are revising. There's not much holiday making going on at Easter. You can go on holiday for 2 weeks if you want. If you can actually go anywhere with the lockdown restrictions, you can take the 2 weeks, but then you've only got a month to revise for 5 hires if that's what you're doing. And I would really suggest that you're doing some hard revision, going right back to the start of the entire physics course and revising very hard, because the final exam is going to be pretty hard, unfortunately. Okay, that's it for now. Bye.